Hi, this is the video for section 3.2 about measures of dispersion. The objectives in this section are 1. Determine the range of a variable, 2. Determine the standard deviation of a variable, and 3. Use the empirical rule to describe distributions that are bell-shaped. Before we talk about those objectives, we need to talk about what measures of dispersion are. So a measure of dispersion tells us how varied or spread out the values in a data set are. Measures of dispersion can only be used for quantitative data. They have no meaning for qualitative data. Range and standard deviation are the two measures of dispersion we will use. As an example of measures of dispersion, here are histograms for two different sets of data. Both of these concern waiting time for customers at two different branches of a bank. So if we look at the two histograms, it looks like this histogram on the left has data values that are more spread out. The class limits for the classes go from 2 all the way up to 10. For the histogram over here, the data is not as spread out. Notice that the classes here start at 3.5 and only go up to 7. So these are more grouped around the center of the data than these ones are. So we would say that the data set on the left has more dispersion than the data set on the right. Our first objective is to determine the range of a variable. So the range of a variable is the difference between the maximum data value and the minimum data value. The formula looks like this. All we're doing is subtracting the minimum value from the maximum value to get the range. The range as a measure of dispersion is very sensitive to extreme values. Another point about the range is that it only takes into account two data values from the set, the maximum and the minimum. It doesn't take into account any other data values. So it is very easy to calculate, but it's not actually as useful as some other measures of dispersion that we can use. Here's an example for finding the range. In this example, we have those same two histograms, and we're going to estimate the range for each of the data sets shown in the histograms. And we say estimate because since we have histograms, we don't know the actual data values. All we know are the lowest possible data value, which would be the lower class limit for the first class, and the highest possible data value, which would be the upper class limit for the last class. So we can estimate the range by taking that largest possible data value, which is 10, subtracting the smallest possible data value, which is 2. So our range estimate here would be 8. Now for the set over here, again, we can estimate that the maximum data value is 7 and that the minimum data value is 3.5. So that would give us an estimate for our range of 3.5. Since the range for the data set on the left is larger than the range for the data set on the right, we would say that this data set is more spread out or has more dispersion than the one on the right. Here's another example of finding the range where we have the actual data values. So these data values show the selling price for a sample of 16 homes sold. We want to find the range for the selling price. We need the maximum and minimum data values. So if we look through this list, we'll see that the maximum data value is 475,000. The minimum data value is 214,900. To get the range, we would subtract those two and come up with 260,100. So this is our range. Our second objective is to determine the standard deviation of a variable. The standard deviation is another measure of dispersion. It's denoted by the lowercase Greek letter sigma for a population, or by a lowercase s for a sample. It's a measure of variation of values about the mean. So the value of the standard deviation is almost always positive. It cannot be negative. The lowest value it can have is 0. And the value of the standard deviation can increase dramatically with the inclusion of one or more outliers. Outliers are, just like extreme values, they're data values that are far away from all the others. And the units of the standard deviation are the same as the units of the original data values. So if our original data is measured in minutes, then our standard deviation will have that same unit of minutes. We're going to look at the formulas for calculating the standard deviation by hand. We won't actually use these formulas in practice, but we're going to look at them and see how they work, just so that we can get a better picture of what the standard deviation is actually telling us. So for a population standard deviation, again that's represented by the Greek letter sigma. What this formula tells us to do is take each data value, which is represented by x, subtract the mean, take that resulting value and square it, and then this symbol tells us to add up all of those results, and then we're going to divide by n, which is our population size, and finally we take the square root. For the sample standard deviation, this is represented by the letter S. This is the same process except that we divide by the sample size minus 1. Whereas with the population we divided by the population size, here we're dividing by the sample size minus 1. Again, we're going to look at some examples of calculating this by hand just so that we can see how different types of values affect the standard deviation and what the standard deviation actually gives us. So here are the results of a random sample taken from the travel time in minutes to work for 5 company employees. So these are our data values, 18, 23, 23, 26, and 28. And we're going to find the sample standard deviation. We're going to use this formula. So the first thing we need to note in order to use this formula is what is the mean for the sample, because that needs to go there. So to find the sample mean, we take all of the data values and add them together, and then we divide by the number of data values we have, which is 5. If we do that, we get 23.6. Now the easiest way to calculate this by hand, if you have to, is to use a table. So we start out with our table and all of our data values. The next thing we do is for each data value we take that value and subtract our sample mean of 23.6. So if we take 18 and subtract 23.6 we get negative 5.6. And then we do the same for the rest of these. So here are our results. And notice here that the farther the value was away from the sample mean, the bigger value we get in our table here, whether it's negative or positive. Now we take each of those values and square it. So this is why the standard deviation can never be negative, because when we're squaring a number, even if it's a negative number, we get a positive value. So all these values are going to be either 0 or positive. And notice that the bigger the absolute value of the number, the bigger the value of the square in this column. So the value that was the furthest away from the sample mean, which was the 18, gives us the biggest value here to add on. So once we've squared all these values, we add up that column, which gives us 57.2. Then to complete our formula, we take 57.2, divide it by n minus 1, our n was 5, so we're actually dividing 57.2 by 4, and then we take the square root of that value. That gives us 3.8, and that is our sample standard deviation. Now we'll look at another example. This came from a different random sample of 5 company employees' travel times. And notice that some of the values are the same, but here instead of a 23 we now have a 5, and here instead of a 28 we have a 43. So this set of data has much more varied values than the other one did. We're going to see what happens when we use the formula here to find the sample standard deviation. Again, the first thing that we need to know is the sample mean. So if we add up these values and divide by 5, we get 23.0. So the sample mean isn't much different than it was for our other set of data. For the other set of data, it was 23.6. Again, we're going to use a table. So here are all of our data values. And first we're going to take each data value and subtract the sample mean from it. If we take 18 minus 23.0, we get a negative 5. And we do the same for the rest of these. Notice for the 23, since it was the same as the sample mean, we got a 0 in this column. And notice for the two values that were the furthest away from our sample mean, the 5 and the 43, we got some pretty big numbers in absolute value in this column. So over here, when we square each of these values, notice these two very large values in this column now. The largest one came from this value that was the furthest away from the sample mean. So when we square that difference, we get a very large value to add on to our total. Now if we total all these up, we get 758. To complete our formula, we take 758, divide by 4, and then take the square root. This gives us 13.8. Again, this value is much larger than the sample standard deviation we got for the other data set. For the other data set, we came out with 3.8 for our standard deviation. Again, this is because our extreme values of 43 and 5 added a lot onto our standard deviation calculation. They added a lot onto our total right here. So that in the end made our sample standard deviation much larger than it was for the other data set. Now, we won't normally be using that formula to find the standard deviation by hand. We'll normally be using technology such as StatCrunch or a graphing calculator like the TI-83 or 84. So to find this with the TI-83 or 84, the first step is that we have to enter the data into a list, and on those calculators the lists are called L1 and L2 and so on. And once we've put our data into a list, then we use the one variable stats function, and that calculates the mean and standard deviation as well as some other values. As an example, we're going to use our graphing calculator to find the sample means and sample standard deviations for these two data sets. So for this first set of data, we are going to put it into the list L1. To get there, on our calculator, we push the Stat button, and then we want to edit, so you can just press Enter. That takes us to our list screen. So now I'm just typing in the values from the data set. So I have 18, 23, 23, 26, and 28. Now to get the one variable stats, press the Stat button again, then arrow over so it says Calc on the top, and we're going to use that very first function on the list, which is one variable stats. So press Enter. Now some of you won't see this particular screen if you have an older model calculator. It will just come up on your regular screen as one var stats. If it does that, just press Enter. Otherwise, just enter through that screen, and then this should come up either way. What we're looking at here is the X bar, which is the sample mean, and the SX, which is the sample standard deviation. Now notice if you scroll down through here, it gives you other information also, such as the median, the min and the max, some other things that we'll talk about later in this chapter. If you want to go back up, just scroll back up using your up arrow key. So now we've found the mean and the standard deviation for that data set. Now let's go back and find it for the other data set, which just had a couple of different values in it. So we can just enter or arrow down until we get to the value that we want to change. So I'm pushing Enter a couple of times till I get down to the middle value, which in the new data set is a 5. So I'm just going to enter a 5 there, and then I'm going to change this last one to a 43. And notice there I made a mistake. I put in 433. I can just arrow back up there and re-enter the value that I want. So it's very easy to correct mistakes. Now I've got my data entered, so I'm going to go back to Stat and Calc and press Enter or 1 to get the one variable stats. And again, if you get this screen, you can just enter all the way through it. If you get the other screen, just press Enter and you should come up with this. So here our X bar is 23, and the SX, which is a sample standard deviation, is 13.8. That's the same thing that we got when we were doing it by hand. Now, if we have two different samples, sometimes we can compare the standard deviations easily, but for some samples that doesn't work very well. So we only want to compare standard deviations for two different data sets if they use the same scale and units, and if they have means that are approximately the same. If we're comparing variation in samples with very different means, it's better to use the coefficient of variation, which describes the standard deviation relative to the mean. The formulas for the coefficient of variation are, for a sample, the coefficient of variation is the sample standard deviation divided by the sample mean times 100%. For a population, it's the population standard deviation divided by the population mean times 100%. Let's look at an example of finding the coefficient of variation. So the statistics below were calculated from a sample of cereals for two different variables: carbohydrates per serving, which is called carbo here, and calories per serving, which is called calories here. So we're going to find the coefficient of variation for each variable. Now if we look at just the standard deviations and the ranges for these two variables, since the standard deviation for calories is much larger, that might make us think that this variable had much more dispersion than the carbo variable. But what we're going to do here is look at that standard deviation as a percentage of, which will let us compare the two much better. So our coefficient of variation for carbo is our standard deviation divided by our mean times 100%, which gives us 26.4%. For calories, we have our standard deviation, 19.48, divided by our mean, times 100%, and that gives us a result of 18.2%. So actually for the calories, the coefficient of variation is less than it was for the carbo. And that tells us that if we compare our standard deviation to the mean, the calories per serving has less variation relative to the mean than the carbohydrates per serving did. Now we can also compare the histograms for our two variables. So here's the histogram for carbo, and remember this was the one that had a smaller range and a smaller standard deviation, but a slightly larger coefficient of variation. And here's our histogram for calories. This one had a much larger range, a much larger standard deviation, but the coefficient of variation was actually less. And if you look at it this way, the amount of dispersion relative to the mean doesn't really look that different between these two sets of data. Again, if you were only looking at the standard deviations, you might think that the calories per serving had much more dispersion because the standard deviation is so much greater. But if you compare it to the mean, as we do when we're finding the coefficient of variation, you can see that it really doesn't have more dispersion than this variable over here. Now the variance is another measure of dispersion, but it's not one that we're going to use much. So all we're going to do here is define it. All we're going to do here is define it in case you run into it and wonder what it is. So the variance of a variable is just the square of the standard deviation. So the symbol for the population variance is sigma squared, and for the sample variance is s squared. Our third objective here is to use the empirical rule to describe distributions that are bell-shaped. So the empirical rule says for data sets having a distribution that's approximately bell-shaped, about 68% of all the data values fall within one standard deviation of the mean. So between the mean minus one standard deviation and the mean plus one standard deviation. About 95% of all the data values fall within two standard deviations of the mean. So between the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. About 99.7% of all the data values fall within 3 standard deviations of the mean. Here's a picture to help make this a little bit clearer. Here is our approximately bell-shaped distribution, and here we have the mean in the middle, and if we go one standard deviation on either side, so if we subtract the standard deviation to get this boundary and add the standard deviation to get this boundary, in between those two values we have 68% of our data values. If we go one more standard deviation on either side, so here we're 2 standard deviations below the mean, over here we're 2 standard deviations above the mean, between those two values we actually get 95% of our data values. And if we go 3 standard deviations from the mean in either direction, between those two values we get almost all of our data values, 99.7% of them. Now, since a bell-shaped distribution is also symmetric about the mean, we have a mirror image on either side, and that's why we can divide these percentages up as they are in this picture. So here we have 68% altogether, but we have 34% on either side of the mean. Let's look at an example of using the empirical rule. So the distribution for IQ scores is approximately bell-shaped. The population mean is 100 and the population standard deviation is 15. So first we'll find the cutoff scores for the middle 68% of the population for IQ scores. Then we'll find the cutoff scores for the middle 95% of the population. Then we'll look at what percentage of the population would have IQ scores between 100 and 145, and then what percentage of the population would have IQ scores below 85. So first we'll find the cutoff scores for the middle 68% of the population. Now, since we have a distribution that's approximately bell-shaped, that means we can use the empirical rule. The empirical rule says that about 68% of the population have scores that are within one standard deviation of the mean. So if our mean is 100 and our standard deviation is 15, then we're just going one standard deviation on either side of the mean. If we go one standard deviation below the mean, that would get us down to 85. One standard deviation above the mean would get us up to 115. So about 68% of the population have scores between 85 and 115. For part B, 95% would have scores within two standard deviations of the mean. So now all we have to do is go two standard deviations on either side of our mean. If we go two standard deviations below the mean, that would give us 70. Two standard deviations above the mean would give us 130. So approximately 95% of the population has an IQ score between 70 and 130. So what percentage of the population would have IQ scores between 100 and 145? If we look at the picture of our bell-shaped distribution in our empirical rule, what we need to do is locate these two values in our picture. So the 100 was actually the mean, so that would be the value right here in the middle. And then for the 145, we need to know how many standard deviations above the mean that is. So if we go up by one standard deviation, we get to 115, then to 130, and finally to 145. So 100 was our mean, and 145 is 3 standard deviations above the mean. Now, since we have the picture with the percentages laid out for us, we can just add the percentages in those 3 spots to get our total. So if we add 34% and 13.5% and 2.35%, we get 49.85%. So that would be the percentage that would be between 100 and 145 for IQ scores. Now, what percentage of the population would have IQ scores below 85? Again, we're going to take our picture and we want to locate 85 in this picture. Our mean again is 100, so that's right there in the middle. If we subtract one standard deviation from that, that's going to give us 85. So here's where the 85 is, and we're looking at what percentage of the population would have IQ scores below 85. So from here all the way to the left. And again, we're going to add up the percentages in these 3 regions to get our answer. So if we add those percentages, we get a total of 16%. That means 16% of the population has IQ scores below 85.